want you to imagine a pulse of energy so powerful, so unbelievably intense, that it just completely redefines what we even think of as power. Today, we're diving into the pretty radical thinking required to build something that can actually survive a direct hit from that.
So that's the big question, right? It's simple to ask, but incredibly hard to answer. How do you design a material to withstand an energy source that, by all logic, should just vaporize it in an instant?
The scale we're talking about here is 1 petawatt. That's a quadrillion watts. A 1 followed by 15 zeros. It's one of those numbers that's so huge it kind of breaks your brain trying to even picture it.
To try and put that into perspective, a single one of these petawatt pulses contains more power than every single power plant on Earth, all of them combined, is generating at any given moment. And all of that energy is focused on one tiny spot for just a fraction of a second.
And that, right there, is what we can call the petawatt problem. It's a challenge that doesn't just bend our engineering rules, it completely shatters them.
I mean, your normal go-to materials, something as simple and reliable as a copper wire, it doesn't just melt here. No, it instantly vaporizes. It explodes from the sheer density of the energy. The entire old engineering playbook is just completely useless.
So to solve this, you need a totally different way of thinking. It's a radical shift. Instead of trying to just resist the energy with brute force, you have to learn how to manage it, how to guide it. You basically need to build a kind of shock absorber, but for electromagnetic fields and electrons.
This quote just captures the new philosophy perfectly. See, it's not about building some impenetrable wall. It's about creating a system that can gracefully absorb and then dissipate an absolutely incredible blow.
And here you can see the two approaches in really stark contrast. You've got the brute force method on one side, a single material that, well, it just explodes. But on the other, you have this idea of a layered stack that intelligently manages the energy and survives. The difference here is all about elegance, not just raw strength.
So what does this energy shock absorber actually look like? Let's get into it. Let's break down the anatomy of this conceptual multi-layered solution. The real secret, the key, lies in this 5-layer stack. And each layer has a very distinct, incredibly crucial job to do. It's designed to handle a specific part of that energy pulse at a very precise moment in time. Let's peel them back, one by one.
All right, first up is the strike layer. You can think of something like graphene here. Its whole job is to meet that pulse head-on and immediately, and I mean immediately, spread that initial violent spike sideways, laterally across its surface. It does this so fast, the material doesn't even have time to heat up. It's the system's first and maybe most important line of defense.
Right behind that is the absorption layer. This could be made of something like carbon nanotubes. So after that initial spike gets spread out, this layer's job is to channel the unbelievable electrical current that follows. It prevents what's called a cascade effect, where atoms are literally ripped out of place that would just tear a normal conductor to shreds.
Now for one of the coolest parts, in my opinion, the transition layer. This is a liquid metal. You see, a petawatt pulse isn't just electrical energy. It carries immense physical force. It's like getting hit with a hammer. This liquid layer absorbs that mechanical shockwave. And because it's a fluid, it can instantly self-heal any voids or damage that might have been created in the layers above it. Just amazing.
Layer 4 here is actually optional. It's for situations where you don't just want to survive the pulse, but you actually need to move that energy somewhere. So if you can keep things cryogenically cold, you can use a superconducting layer to transport that massive current with absolutely zero resistance. And zero resistance means zero heat buildup, which is, a major reason things fail.
And finally, we have the ultimate safety valve, the sacrificial layer. And this is genius. If the system is still overloaded after everything else, this layer is actually designed to fail, but to fail gracefully. It intentionally turns any excess, totally unsurvivable energy into a controlled channel of plasma, which protects the rest of the structure. So, we've seen all the individual parts, we've met the whole team. Now let's see how they all work together in this perfectly timed cascade to actually survive the pulse. The whole sequence of events happens on a time scale that is just almost impossible to imagine. In the first quadrillionths of a second, we're talking femtoseconds to picoseconds, the strike layer does its job. Then, the absorption layer takes over for the next little bit. As the physical shock arrives moments later, nanoseconds to microseconds, the liquid layer kicks in. And if, at any point, the system gets overwhelmed, that plasma layer engages. It's like a perfectly timed symphony of survival. This whole architecture, this whole way of thinking, It reveals a brand new and frankly a very counterintuitive set of rules for handling extreme power.
At these scales, get this, thin beats thick. A big, bulky material just explodes. It's the interfaces between the layers that become more important than the materials themselves. Spreading energy sideways is way more critical than trying to conduct it forward. And maybe the biggest takeaway, creating plasma isn't a failure. It's a planned, controlled safety state.
And this all brings us to a really profound insight. At this level of power, you're not building a wire anymore. The whole concept is wrong. You are architecting a system that is specifically designed to manage the transition of energy from an electron flow into a plasma state, all without destroying itself in the process.
So that leaves us with a pretty fascinating final question to think about. If we can solve the petawatt problem by designing for graceful, controlled failure instead of just old-school brute force resistance, what other impossible engineering challenges could we solve with that very same philosophy? What else can we build?